Hello, my name is Stella Biederman. I work at Booz in Hamilton, and I'm here to talk to you about verifiable computation. First, a little bit about me. So Booz Allen is a consulting firm, mostly with the US government, and I do research and development, creating tools for software engineers and data scientists to use in support of their mission. So I am more focused on the research side of things, and what I've come to talk to you guys about today is some very exciting research that I've been a part of and that I think is becoming a real-world applicable and very useful technology to be aware of. Sorry. So just to give you a quick overview of what I'm going to do, I'm going to give you guys an introduction to the field of verifiable computation. I'm going to tell you what the problems are and why we care about it. I'm going to tell you about, so right now we have mostly working solutions for real-world deployment. So I want to give a little bit of a description of what we wish we had and what we need to do to get there. I'm going to give an overview of the three major categories of verifiable computation, as well as a discussion of what the state of the art is and for what applications this technology is ready to be deployed right now. And then I'm going to conclude with a couple major takeaways. So if you want to take a nap and just tune into the last slide, that's totally fine. So the core question for verifiable computation is, if someone else does a computation for me, how do I know they did it correctly? Nowadays, we see people distributing computation to other computers and other third parties all the time. We see it in cloud computing. We see it in the Internet of Things. We see it in distributed sensor networks. And usually when this happens, the person who is in charge, the person who's getting the results of the computation does not own all of the different devices that are being used, or those devices are accessible by other people. For example, I'm going to talk about voting machines, where tons of people have access to voting machines. And there's a concern that even if you do own your own voting machines, when they're out in the world being used, they might get compromised. And so the core concern is, if you have computationally intensive tasks you want to do, and you want to outsource that computation to other devices that you don't have complete control over, how can you guarantee security or privacy of your data? I'm going to skip that. So what got me into verifiable computation is a paper called Safety Nets, Verifiable Execution of Deep Neural Networks on an Untrusted Cloud, which was published at NeurIPS in 2017. And I read the first couple of sentences of the abstract, and I said, wow, I want to work on that. Sorry. Inference using deep neural networks is often outsourced to the cloud, since it is a computationally demanding task. However, this raises a fundamental issue of trust. How can a client be sure that the cloud has performed inference correctly? A lazy cloud provider could use a simpler but less accurate model to cheat and reduce its computational load. Or even worse, a malicious actor could deliberately mislead you about the results of your computation. And in this paper, they put forth a protocol that can be used to determine whether or not clouds have executed certain types of neural networks correctly, even when the neural networks in the data they're being used on are far too large to use on your own computer and far too large sometimes to even store on your own computer. Now, there are a lot of different security issues that arise in distributed computing. And so I want to emphasize what I'm not going to be talking about. Malware detection, network security, loss of data, loss of access control are all pressing problems in distributed computing and cloud computing. But they're not going to be what I'm going to focus on. I want to focus specifically on how do we know that the answer we're being given back is actually being truthfully reported and was correctly calculated in the first place. We can break this down into a couple different types of questions. So in the example of an AI model deployed on the cloud, you might wonder, are they actually using the data I provided as opposed to doing inference on other data? Are they actually running it through the model I asked them to run it through as opposed to running it through some other model? Are they using the model correctly? Maybe it was misimplemented by accident. And then finally, at the end of all this, you can wonder if they actually reported the result to you correctly. We can ask similar questions, for example, about databases, deployed on the cloud. So I've talked a little bit about applications, and I want to talk about that a bit more because one of the really interesting things about this field is how diverse the different applications are and how diverse their needs are. So you have cloud computing, where you have things like databases and neural networks deployed on the cloud. And you want to know that the person who owns the cloud is correctly and truthfully reporting the answers to your computations. You have in situ computation, where you take small devices and put them out in the world. And oftentimes they are accessible or deliberately interact with other people. You want to be able to make sure that they're not being tampered with and that they're able to accurately report the results to you, even if someone tries to interfere with that. You have citizen computation, which is a growing trend in academic research, at least, where people volunteer their computer free time to help researchers solve problems. So for example, GIMPS is the Great Internet Mersenne Prime Search, where you can go to a website and when your computer is idling, volunteer it to do brute force computations to try to find large primes. SETI at Home is a similar project where you're helping a collaboration of different universities identify planets that might be hospitable to human-like life from all of the satellite images we have of deep space. And finally, blockchain. Blockchain is actually a really interesting application for this because blockchain, the underlying technology in blockchain arose out of interest in verifiable computation. Its specific goal is to provide a publicly verifiable and distributedly stored database. So in a variety of different applications, we see issues arising from errors or from sometimes deliberate fraud. For example, in environmental monitoring, there's a lot of small-scale devices that people use to measure pollution, to measure toxins. In 2018, the University of Chicago determined that environmental monitors that had been placed in a river in India were reporting fraudulent information. Not that the government had done anything, but the individual fishermen had been concerned about what would be reported about their activities, and so deliberately modified the devices to report their answers incorrectly. There's been a lot of concern in the news. There was a Senate hearing. There's been a lot of concern in the news recently about voter fraud, about voter machine issues, where you want to make sure that you know that the votes are being tallied correctly, that the data is being stored securely. At DEF CON in 2017, a wide variety of different exploits were very, very publicly demonstrated about this. When it comes to citizen computation, sometimes people participate in these programs and just deliberately mislead people. In 2013, GIMPS actually announced M40, which is the symbol for the 40th Mersenne prime, incorrectly. They never quite figured out exactly what happened, but one of the primary hypotheses is that the people who were performing the computations, as well as other people who were checking those computations on their own devices at home, decided to incorrectly report the result. It was eventually caught and the announcement was retracted, but it was quite sad and vaguely embarrassing. And just as a little fun fact, I wanted to share that that is the largest known prime. It's a very, very large number. Photography verification is a big issue that we see in the news and that there was even a Senate hearing on yesterday when it comes to deep fakes. Fake photos go viral all the time, and more we see news sources relying on local correspondents and individual citizens to report news events to them. So one topic that's received a lot of interest in research is, can you build a camera that will somehow guarantee that the photo was taken in the location that you claimed it was, or somehow guarantee that a photo was taken at the time that you said it was? And blockchain and cryptocurrency is a direct application of this in its entirety. But there have been a variety of different setbacks. Ethereum is a blockchain that allows you to basically pay people to run code for you. You write digital contracts, and then you pay them money, and then they run the code corresponding to that contract on their computer. An exploit in the way the security protocols were designed was found in 2016, and someone stole about $50 million. Zcash is another blockchain. This time its orientation is more towards allowing private but still verifiable computation, where their key idea is that they want individuals to be able to have person-to-person private transactions that are not disclosed to any party, but at the same time be able to comply with anti-money laundering laws, tax regulations, and things like that. Ariel Gabizon discovered that there was a hole in their protocol that allowed him to clone money in 2018. Very fortunately for Zcash, he works for Zcash, and they closed it within a week. So verifiable computation has been a topic that people have been talking about for a very long time, mostly theoretically in academia. But the most important result for our purposes is the bolded one, interactive proofs for muggles in 2008, which was the first vaguely real-world applicable version of these kinds of protocols. Although they had been designed in theory 2 decades earlier, for example, for most real-world computations, the protocol that for the PCP theorem would take longer than the expected lifespan of the universe to run. Not exactly something you can actually deploy. So because we have a lot of different contexts, we also have a lot of different things that we might care about. There are 3 essential requirements that we're going to want in basically any context that we care about verifying computation. First of all, we want to be able to verify the computation was correct. That's the whole point of the exercise. Secondly, we want the verification to be confidential. We don't want the people who are reporting information to us to know what we determined about whether or not we thought that their answer was correct. And thirdly, we want to be able to do this extremely, extremely quickly. The vast majority of the time that we distribute computation, it's because we don't have the computational power to do the computations on our local devices or on just one device. And so when we're running a verification scheme that we need to run on our own device, we need it to be much, much, much faster than the actual computation itself can take. And that is a crucial hang-up and point and the main focus of current research about just how fast can you verify computation. And there's a lot of different things that, depending on your context, might be nice to have. Zero knowledge verification means that during the course of verifying the computation, you don't leak any information to other parties. As I'll talk about, most of these protocols are interactive, where you go back and forth talking with the people doing the computation for you. Public verification is extremely important, especially in the application to, for example, algorithmic decision making. The US government has recently been talking about moving some of its decision-making algorithms to cloud-based servers. And one dream that you might have for this is that they'll be able to implement a protocol so that any person can go to a website, download some data, run it on their computer, and confirm that the formula that the cloud server says is being used to calculate, for example, unemployment benefits is actually what they're doing. This can have very big implications for transparency in government and for various other applications. I said a lot of these protocols are interactive, and that incurs communication costs, so skipping that is nice. And the other couple have to do with more technical details that I'll get to in a bit. So there are 3 major ways that you can verify computation. They're called interactive proofs, interactive arguments, and non-interactive arguments. An interactive proof is a back and forth conversation between you, who is sending out requests for answers to questions, and the device or devices that are answering them. So you send out a query, for example, what happens when I run a neural network on this data? And they send you back the answer. And then you basically get to interrogate them on the computational process itself. You ask them follow-up questions, and they provide you follow-up answers. And these communications are designed so that when you have enough of the answers together, either the remote device is forced to contradict itself at some point, or you're able to guarantee that the result was done correctly by eventually reducing the question of was this done correctly to a much simpler question that you're able to check on your own. Interactive proofs are one of the more promising avenues for real-world application, and many of the actually real-world applicable solutions rely on them heavily. They have complete correctness, and they have complete confidentiality. And they are extremely fast-ish. They're extremely fast for the right kinds of computations, and that's one of the big limitations we'll see. Exactly what you need to compute can affect whether or not you can actually verify it reasonably. It's easy to publicly verify them, and it's very easy to parallelize them, the actual verification. So if you have a small server at your company, you want to verify a cloud computation, you can spend less work on each individual device. An interactive argument is sort of the reverse of an interactive proof. Instead of someone explaining to you their computational process, they want to convince you that they know the answer. And the way that they do this is by presenting you with partial explanations and partial arguments, as well as cryptographically making commitments, promising that certain things are going to come out true at the end, no matter what follow-up questions you ask them. Interactive arguments have the most problems of the three major avenues for application. In particular, they are not that fast, and although they're on par with the actual computation themselves, they aren't fast enough to be deployed in most applications in a realistic fashion. They also sometimes have issues with actually verifying correctness. Sometimes you can get close to that, like you can verify that they knew the right answer, but not that they told you the right answer. And finally, we have non-interactive arguments. Non-interactive arguments have been the source of a lot of very recent research due to a variety of breakthroughs pioneered by, amongst other people, blockchain researchers. In non-interactive arguments, the computational device lectures you. It provides you with a ton of different information, and you are able to put that together and verify that the answer to your question is what they claimed it to be, based on each of these different arguments, which are individually designed to convince you of the truth of a particular fact. These are extremely fast. They are by far the fastest application that we have today. And they have another number of auxiliary useful processes. For example, public verifiability. They don't require extensive communication. It's a one-time message that you receive. And in many applications, they don't quite get complete correctness, but they can get statistical correctness. You can be 90% confident that the answer was right. And oftentimes, that's good enough for practical application. And if it's not, you can do it twice. And then you're 98% sure that they did it correctly. For general purpose computation, the state of the art is something called the Pepper project out of the University of Texas, Austin. It has made massive breakthroughs on the theoretical complexity of verifying general purpose computation. They introduced a specific paper that decreases the runtime by a factor of 10 to the 20. Unfortunately, like I said, they're comparing it to something that finishes after the universe ends. So even a factor of 10 to the 20 doesn't necessarily make it real world applicable. It is down to the order of less than a year, though, depending on what exactly you're doing. And they're hopeful that they're going to be able to get this general purpose approach that can be used in any context down to days or hopefully one day hours relatively soon. For neural networks, there isn't any general purpose approach, but for different questions that you care about, there are partial solutions. For example, for encrypted data, maybe you have information that you want someone to analyze for you, but you can't give them access to the information at all. Instead, you have to send them an encrypted form of the information. The protocol works pretty well. It runs quickly. It introduces minimal overhead. The current problem with this solution is that for very large-scale data sets, it requires too much communication. This is sort of intrinsic to the setup because you have encrypted data that you actually need to send them. And if you don't send them most of the information, then you're not actually allowing them to do the computation. The researchers for Faster CryptoNets analyzed their software on an extremely large medical research database and found it required almost a terabyte of communication. For certain kinds of circuits, the paper safety nets has the answer. The cloud computer that is doing the inference for you increases its runtime by about 1%. And it takes your computer locally about 3 seconds to verify it, regardless of how big your network was and regardless of what the data was. The problem is you can't use this for most computations. It requires you to use specific kinds of activation functions and neural networks that have specific properties. And another major point of research is collaborative, where you have data sets distributed amongst multiple parties, and they are interested in allowing you to see their information, but aren't interested for the purposes of inference, but not interested in allowing the other half of the data owner to know their half. For in situ computation, there's just too many variables and too many contexts to have a general purpose approach. But for many applications, this is actually a completely solved problem. Voting machines, in particular, are a 100% solved problem from a computer science point of view. The main issue when it comes to the security of voting machines, besides the fact that I don't actually know of any country that has implemented these protocols that have existed for 3 decades, is physical security and hardware challenges. You need to actually make, the most secure algorithm in the world isn't going to help if you allow someone to put a USB drive into your computer. And a variety of actual studies on voting in the United States have found that, yes, you can walk up to a voting machine during an election and put a USB drive in it and access information on the machine. So there's a lot of real physical security and hardware challenges that remain. When it comes to citizen computation, we have also seen a lot of real progress. In particular, basic data science is mostly a solved problem. If you want to verify that someone did matrix computations correctly or basic number theory computations, that's easy to do and readily downloadable off GitHub. There's at least 3 repositories that have it implemented. The problem for data science and for distributed data science is statistics. There are somewhat deep philosophical and conceptual issues around the idea of verifying statistical analyses. In particular, this relates to the kind of reproduction crisis in science, where someone can run a lot of statistical analyses and only report one of them to you, the one that shows the answer that they wanted it to show. And because there is some random chance in statistics, that causes problems. And there isn't really a known framework for even approaching this problem yet, which is pretty disappointing. People have been working on building cameras, like I said, that can actually guarantee that photos were taken where they are claimed to have been taken and when they're claimed to be taken. But there are some logistical challenges remaining. One of the big ones that came out with some recent research I was reading was that people were doing this by basically embedding a very complicated watermark inside the photographs. Unfortunately, they were developing these cameras for journalists to use. And if you're publishing the photos, you're publishing them with the watermarks embedded in them. And then other people were able to read those watermarks and reverse engineer what the verification algorithm is. Blockchain is a complicated example. There are a lot of successes that blockchain has had. And there's a lot of excitement about using blockchain to verify computation. But there is a lot of different problems. For arbitrary contracts, Ethereum is the best approach. It works. It seems to be safe since 2016, but it is really expensive. The way that Ethereum gets around the fact that verifying arbitrary computations takes a very long time is by making everyone on the blockchain do it. And unfortunately, you have to pay those people to do it. And for private transactions, the Zcash application that I discussed, again, they had a security hole discovered about 6 months ago or 8 months ago. So it's a little bit questionable whether or not it's currently accurate, but currently seems to be accurate. So what does verifiable computation mean for people who are actually interested in implementing systems? I think the most important first question is, if you use distributed computing, if you use cloud computing, if you use the Internet of Things or sensor networks, have you seriously considered whether or not the information that you're being passed by those auxiliary devices is correct? Oftentimes, there isn't actually a real reason to be skeptical of trust. For example, the vast majority of cloud databases are hosted on a handful of servers owned by very well-known and respected companies. And there is implicit trust in the fact that Amazon or Google or Alibaba isn't going to maliciously lie to you about your computation. And if you have trust in your context, that's great. That means you get to skip all the hard stuff. But it's worth thinking about whether or not you have that trust and what risks you are potentially exposed to if there is a problem with your distributed computing. Another major takeaway is that different techniques work best for different circumstances. This is unfortunately an area that doesn't yet have a kind of one-size-fits-all solution. And it takes some work to actually decide whether or not there is a solution for your particular context. Sometimes that is work worth doing. Sometimes, depending on what risks you've assessed, it's a bit too much work. But it's definitely something that's important to be aware of and to investigate. And the final major takeaway is I want to get people excited about this area. I think this is a very interesting and very potentially impactful technology that has begun to develop in the past 5 years for real-world application and is continuing to develop. Actually, while I was writing this presentation, I came across a new paper that came out like a month and a half ago, and one of the state-of-the-art applications I mentioned didn't exist the last time I was thinking about verifiable computation 2 months ago. So I hope this sounds exciting and you guys are interested in keeping an eye out for future developments. And I went through that very quickly. Does anyone have any questions? No? Yeah. So okay, so how do you do it? So different approaches work a little bit differently, and some of them are extremely complicated and would be an hour-plus lecture on their own to explain. The neural networks are a particularly accessible example of a relatively simple algorithm that you can actually use to verify computations, as I said, as long as your neural network kind of has the right structure. What happens in a neural network is you have information that cascades forwards through nodes, getting added and multiplied and combined. And at the end, you end up with an output. In order to verify that this has been done correctly, what you basically do is you require that the person doing the computation promises you information about what's going to happen in the future. So you say, trace a subset of your network from the beginning to the end and check individual computations along the way, skipping most of them. But you make them pre-commit to what the answers to those queries are going to be before you choose which branches you follow and which paths you follow. And this allows you to basically require them to have constructed the entire network tree in order to correctly answer your questions about individual nodes. The way you can actually use this to verify computation, though, instead of just proving that they did the right work, is that the very first node is something that you can very easily calculate. Because the very first node in a path through a tree is just a single matrix computation, and you can do that on your own computer. And so what you do is you kind of trace backwards. So you have their statement about the entire computation through the tree, and then their entire computation through the tree minus the last row of nodes, and then through the tree minus the last 2 rows of nodes, and set up in such a way that each promise is, if one promise is correct, then all of the other ones are as well. And so you follow this backwards, unwinding the tree to the very first layer, which you can verify by doing a single matrix multiplication.
Would it depend on how deep your neural network is?
Yeah, so how long it takes depends, and in particular, how many rounds of communication it takes, because this is a back and forth conversation, depends on how deep your network is. And there are a couple ways to kind of cheat and jump forward, but in general, you're going to need about as many communication rounds as you have layers to your neural network. Fortunately, that tends to not be a huge limitation. Even 30 rounds of communication, if the communications are relatively short, is not a very big computational hurdle. All right, thank you for coming.